video will cover section 10.1, which is the first video of chapter 10 of our pre-calculus book. Chapter 10 is a very diverse chapter because it covers like a little bit of everything that you will see in other math classes. So we're going to cover a little bit of proofs by mathematical induction. It's kind of like what I have on the board over there. Don't be scared yet. And then, but sections 10.1 and 10.2 are fairly easy. And those two will be on your test, okay? And what we talk about are sequences in 10.1, like an intro, and then 10.2 is a specific type of sequence, arithmetic, and then 10.3 will be geometric sequences. When do you see them again? Well, you need them like for computer science or for calculus. Calculus 2 specifically. And they're kind of easy one to work with. So one of the most famous ones is the Fibonacci Sequence, which is named after Leonardo of Pisa, also known as Fibonacci, and he was an Italian mathematician of the 13th century. So the Fibonacci numbers are like very special because they can be seen in nature patterns. So, for example, the arrangement of the individual florets in the head of a sunflower forms spirals. In some species, there are 21 spirals in the clockwise direction and 34 in the counterclockwise direction. 21 and 34 are Fibonacci numbers, like you can see here. I don't know why this is. Oh, there you go. And so the precise numbers depend on the species of the sunflower. 21 and 34, or 34 and 55, or 55 and 89, or even 89 and 144. As you can see, those numbers are part of the Fibonacci sequence. This observation, well, we already have that. Now, let's see how that, yeah.
Isn't there a symbol for Fibonacci or whatever, and it's like a horn or something? It looks like a horn.
Like what?
Like it's like spiraling, but with like lines in it.
Maybe you might be thinking about the golden ratio, like that, and then like it has like a spiral here. No. Okay, you might be right. I don't know the symbol for Fibonacci. But what I know is how they get the numbers. So, for example, the first term and the second term are given to you. And it's just the first term is 1. The second is 1, always. So then the third one will result from the addition of the first two. So 1 plus 1 is 2. Then we get 1 plus 2 is 3. And then we get 2 plus 3 is 5. And then 3 plus 5 equals 8. Oh my God. Actually, Mr. Sturga and I, that was one of our online exams passwords. I told him the first 5 Fibonacci numbers. Yeah, and that was the password. You shouldn't sign us that. That's password. But yes, 5 and 8, 13. 8 and 13, 21. 13 and 21, 34. So this is also like a recursive sequence, which we're going to study in a minute, okay? And in fact, it's kind of, do you guys know where he came with this? The first nature that he observed? Rabbits, giving birth to other rabbits. And so that's why you start with a 1 and a 1, because you need a male and a female rabbit. And so what he found out is that they will have 2, but then they will mate with, like, I know it's kind of gross, yes, and then they will have more rabbits, and that's how the population of rabbits was grown. That's how he figured it out. Also, you can see that pattern in spirals on pine cones and pineapples. Yeah, so 8 and 13, that's like the common one. Okay, so, oops. Did anyone have questions? No? Okay, so Fibonacci sequence, we already explained what it was. Let's just write a little something there. So, no, it's fine. We have the definition on the first page. So let's just move on here. So the domain of a sequence is going to be the set of counting numbers or natural numbers. And that is also going to denote the position in the sequence. So for example, the first term, the domain for the first term will be 1. The domain for, and we know the range will be, of course, the output, right, of the sequence.
So be 1.
So this is like the actual sequence term. Not the order, but the sequence term. So going back to Fibonacci, the first term was a 1, right? Second term is also a 1. Third term was a 2. Fourth term is a 3. And then 5. And that here's a coincidence that the fifth term is equal to 5, but it doesn't have to be that case. We could also have, for these terms, we could have negative numbers or whatever you want, but for the domain, it's only natural numbers. So the sixth term was 8, and then the seventh term was 13, and so on. Now, what does this imply? It keeps flowing, right? So that is what we call an infinite sequence. Okay, and the domain, again, is the set of natural numbers or positive integers. So when we talk about a function, we could consider a sequence like a function. But for a function, for example, the domain will be here, right? So f of 1 is 1. Going back to Fibonacci, f of 2, like the second term, is 1. And then f of 3, the third term, was a 2. And then, you guys see the subscripts here? So those are going to tell us the order of the term as well. Just to finish this, f of 4 is 3 for this one. And then f of 5 is 5 for this one here. And then the last one, f of 6 is 8. Yeah, so you can consider them like functions, but as we're going to see on the next slide, they're going to be discrete functions. So let's just write it here. The graph of a sequence is a set of discrete points. So like in Algebra 2, we covered something like graphs that are continuous, and then graphs that are only points. We call them discrete graphs, or discrete functions. So that's what a sequence is. Oh, you don't have the back? Oh, yeah, I'll get you. All right, so going back to this one here, we're going to use the subscripts. The subscript, it denotes the order or placement in the sequence, just like what we call the domain. Okay, so just get used to saying like a sub 1, a sub 2, a sub 3, a sub 4, which we'll be referring to the first, the second, the third, and the fourth. Okay? Now, what is the opposite? If something has an end, the opposite of infinite is what? Finite. Very good. So finite sequences have a specific number of terms. Sometimes we don't know how many are there. Like we don't know if they're 5 or 10 or 100 or 1,000. So to generalize that, we just use the letter n as a number. So we could be talking about the 100th term or the 200th term. So what we will use is the n term. So get used to that concept, okay? So when I say the n term, don't look at me like I'm crazy. Okay? That's it. Only for finite. If it's infinite, there's no last term.
So nth term isn't it? There's still some.
I think so.
Yeah, we used it.
Yes. Okay, so let's find the first four terms of the sequence. It's very simple. So what we're going to do is substitute the subscript and the n over here, just like we do with a function. So a sub 1, it will be 3 times 1 plus 4. So that will be 3 plus 4, 7. A sub 2 is going to be 3 times 2 plus 4. So that will be, 6 plus 4, 10. If you want to do them on your own and then check with mine, that's perfectly fine. So 3 times 3 plus 4, 9 plus 4, and that is 13. Next one, 3 times 4 plus 4, so that will be 12 plus 4, and that is 16. Now for the next general term, this is what we call it, the one that has a formula in terms of n. For the next general term, we're still going to find the first 4. However, here we have to substitute the n here on the exponent for the numerator and part of the denominator. So we have -1 to the first power, and then we have on the bottom 3 to the first power minus 1. Now this will turn into -1, and then on the bottom we're going to have 3 minus 1, which is 2. That's my first term. My second term is going to be -1 to the power 2, 3 to the power 2, and then minus 1. So what happens when I square a negative? So negative, positive, so this will be positive 1. On the bottom, I'm going to have 9 minus 1, which will be positive 1 over 8. The next term will be -1 to the power 3, and then 3 to the power 3 minus 1. So here, what happens when you have an odd exponent? Negative stays negative. So -1 over
8.
27 minus 1.
Oh, right.
So 26. And then the last term, well, not the last, but the fourth, because that's all we were asked to find. You already know that if we have an even exponent, what's going to happen to the -1?
It's going to be positive.
Positive. So that will be positive 1 over 81 minus 1, which will be 1 over 8. So you can see, and we call this an alternate sequence. And this is just like a really good trick when you want your signs to be alternating, like from negative to positive, negative to positive. To use -1 and then just change the power around. Okay, so next slide. So recursion formula. Let's write that definition, please. Okay, so it defines the nth term of a sequence as a function of the previous term. So for example, if I say my 10th term, which is the term that I need to find it? The one before, right? So it will be the 9th term. So if I talk about here to find the nth term, what is the term before? How should we call it? It will be the, anyone?
M minus 1.
Well, m, that's a good reasoning actually, yeah. And n minus 1, yeah. N minus 1. Do you tell me m because that was the letter before? Well, there. Maybe so.
Oh, yeah. It is.
Yeah. So it will be the n minus 1. Okay. So let's find the first 4 terms, and I think that will be all we have time for. That's okay. So we have the first one here. They have to give us something to start with. Fibonacci is, like I said, it's recursive, but you need the previous 2, not just the previous 1. So then here to find a sub 2, I'm going to follow this formula here. So it says you will need 3 times the a n minus 1. So that will be my previous one, which is a sub 1. And then I still need to add a 2. So my previous term, right, it goes there. So 3 times 5 plus 2. So that would be 15 plus 2, which is 17. Then for the third term, we will need 3 times the previous, which was a sub 2 plus 2. Now we know from here that a sub 2 is 17. So we substitute that a sub 2 with the 17 plus 2. And that will be 51 plus 2, so 53. And that is our third term. So now to get the fourth, we're going to need to bring back the third, the previous one. So 3 times a sub 3, we substitute that with the number 53. That will be 159 plus 2, 161. Yeah. So we'll stop here because I don't want to rush through the other part. Did I give you the copy of the second page? No? Okay, good. Then you guys lose it. So I'll give you that next class.